All right, so thank you for watching our video recap. So for those of you who missed on Monday, that would have been October 28th, or today, that's October 30th, I'm making this kind of video recap of the two sections that we covered. The goal being to kind of briefly, or as brief as I can, just give you a little bit more of a hands-on walkthrough of the two filled-in notes. Right now I'm sharing my screen. You can see I have the 6C filled-in notes up in front of me. For you to follow along or fill in your own, you can get the 6C notes here and the filled-in ones right here on Canvas. This is just in our week 11 folder on Canvas. And then the 6D filled-in notes are right here. I actually merged together the agenda in the 6D notes. You can get that right here. That's not the filled in though, that's just the blank one, but that's what everyone got in class today. I can give you a copy of that on Monday as well, but kind of the deal with this was that nobody had actually made 6D notes for me to use. Usually I can pull from a folder rather that has our notes, but there weren't notes for 6D that anyone had made, so I just made my own and added it to our agenda. We went through it as a slideshow and filled in all these examples. That's kind of the second part of this video. So hopefully, maybe if you only missed Monday, but you were here today on Wednesday, then you can probably tune out after I get through the 6C notes, which should roughly be like the first half of this video. Or if you were here Monday and then missed today, I don't think there were really any of you where that was the case, but it could have been. And I might just be forgetting, so that you can just kind of maybe skip through 6C and get to the 6D part. But either way, I would say it'd probably be a good review of both sections, so maybe just stay tuned. Okay, so let's go through 6C first, and I'll be able to kind of the reason why I pulled them up in this fashion in Adobe Reader is so that I can kind of annotate and draw things for you guys. Here's a smile. Okay, so I'll kind of annotate things in red pen as I'm talking about them. You all know that I'm kind of a hand talker, so this is my way of doing that. So, all right, let's start with 6C. So it's about the normal distribution, which is defined as a symmetric bell-shaped distribution with one single peak, and that single peak corresponds to the mean, median, and mode of the distribution. Remember, when the mean and median are equal, that's actually how we defined symmetry of a distribution. Okay. So these distributions are symmetric. That's what they tell you right here in the definition. Okay, so the first example was just differentiating between two distributions, and the question here is just basically which one is normal and which one is not. And if you've seen the normal distribution before, it does kind of look like what we have in A. That's kind of what the distribution, mine is a little wavy. I'm just working with like a little stylus pen here, so I'm not gonna make like the most accurate doodles in the world here, but that looks normal. That's like a bell-shaped distribution. I would say that looks like the normal distribution. Here, if you were to kind of fit this distribution, it looks like it's, looks like I'm zooming in now. It's actually not such a bad thing, maybe. Okay, that distribution kind of looks like that. It's very, see, I always get these backwards, but it's skewed right. It's right skewed distribution that we're looking at here in B. So you can see my answers. A is normally distributed, roughly normally distributed based off of the data and based off the picture we're seeing. B, pretty clearly not normally distributed. Okay, it's for one thing, it's not symmetric. And that's kind of the main problem here. It kind of has the bell shape, but only half of it. Okay, some more conditions for a normal distribution. Kind of what were our takeaways from example one? How can you differentiate these things in general? So a data set satisfying the following criteria is likely to have a nearly normal distribution. So most of the data values need to be clustered near that mean. We definitely saw that in part A of example one. And the distribution should only have one peak. A normal distribution is never going to be bimodal. It's unimodal. That means one peak. So kind of a definition review there. The data values spread evenly around the mean. It makes the distribution symmetric. The larger deviations get really rare, so that's why normal distributions kind of tail off at their curves, and that when it tails off and gets down close to zero, or down close to the axis, that means that there's very low probability in those regions. Okay. Individual data values result from a combination of many different factors. That's kind of true for any distribution, to be honest with you. Although not always. Like what they're saying here, like, for example, if you were to measure height, before we were looking at like chest size, I believe, or actually maybe we're about to look at that. No, I think we were just looking at that in example one. Let's see if I can scroll up a little bit here. Yeah, in example one, we were looking at chest size for Scottish militiamen. That's normally distributed. That kind of, so to tie in number 4 here of these criteria, like the size of someone's chest depends on a lot of things, not just a single thing. Okay, that's probably enough about that. So example 2, kind of again, which of the following variables would you expect to maybe be from a normal distribution? Which ones would not be normal? Okay, so in part A, the scores on a very easy test. The distribution for that, so I'll kind of say that's a pretty ugly A, but you get the idea. That distribution on a very easy test might look kind of like this. It would kind of have a blip. Nah, that almost looks normal. Let me redo that. It would have a blip at its end or at its tail, where maybe this is like a pretty high score, like a 9 or something. Okay, so again, this wouldn't be normal because it's so skewed off to the right there. Okay, and let's see, in part B, so scores on a standardized exam like the SAT, we would expect that to be normal. Standardized exams are typically designed so that the scores are distributed as a normal distribution. There are a lot of reasons for that. As well, like shoe sizes for a random sample of adult women, that's another thing that we would expect to follow a normal distribution. Kind of think of like the chest size of the militiamen, not too different from that example. Like any kind of measurement, like arm length or like size of hands, things like that. Those would probably be normal because most people should like kind of land somewhere close, and then the deviations kind of go to either side and tail off. I really want to redraw my distribution in part A again. It's just bothering me. It still kind of looked normal. So here's kind of like a more extreme like sketch where I have like no people performing poorly. Everyone maybe performs highly. Let's even just put in another mode around like where 10 is. So that's like clearly not normal. Again, now I'm like thinking about part A and just how bad that sketch was. So there's like kind of a corrected one that's a little bit nicer. In part B, you would expect normal distributions, a nice bell-shaped curve in both cases around some value that's common. They tail off to either side after that, okay? So moving on now, let's talk about the 68, 95, 99, 7 rule. I'm just going to look right at the picture for this. I'll include some of the text here as well. So this is a rule for normal distributions only. It's not going to apply to other different types of distributions, really just the one that we're focused on in this packet and in this unit. Okay. I skipped the definition of standard deviation up there in the context of the normal distribution, but we're going to really talk about that here. So keep in mind that a standard deviation, we're going to abbreviate that with that sigma symbol, which you see a bunch of those down here, where, for example, at this plus sigma, that means plus 1 standard deviation away from the mean, and then minus 1 standard deviation away from the mean. The 68, 95, 99, 7 rule says that 68% of our data lies in this first band, where we're on 1 standard deviation to either side at the most. 68% of your data will fall in that first band here. In the second band, oops, now I'm messing with that other line there, which we can just get rid of. In the second band here, where we're plus 2 standard deviations away and minus 2 standard deviations away, 95% of the data lies under that part of the bell curve. And then finally, 3 standard deviations to either side, actually 99.7% of your data falls into that range. Okay. So this has to do with symmetry. It also has to do with other results about just what the curve kind of ends up being. Now, keep in mind, normal distributions, they don't have to always have the same standard deviations. Like you can have very high variation normal distributions. That's a normal distribution. Here's its mean. Maybe here's a standard deviation to the left and right. Like, so you can have wider ones. You can also have ones that are even like more peaked. Like, that's a normal distribution. And now you can see why I kept wanting to redraw that one in part A, where it still was kind of looking normal in a certain way. Okay, so they can look different. They don't always have to have like the same sort of like width. Okay, so the standard deviations could be huge. You could have like this very like wide normal distribution. There's nothing that says we couldn't do that. But the 68, 95, 99, 7 rule is a good way to approximate like how much data falls within certain bands of this distribution. And like I said, it really only applies to this distribution. It's not other distributions, right? So it's the 90, or I always say it a little wrong here, but no, the 68, 95, 99, 7 rule for a normal distribution. Okay, so I think I've emphasized that point like 5 or 6 times. Let's go on and look at an example, see how this is actually used in practice here. So example 3, vending machines can be adjusted to reject coins above and below certain weights. As it turns out, the weights of quarters in the US have a normal distribution with a mean of 5.67 grams and a standard deviation. That's what that little sigma was. So our sigma here, which you can see I've used that little symbol, that's a sigma or a standard deviation of 0.07. The question is, if a vending machine is adjusted to reject quarters that weigh more than 5.81 grams and less than 5.53 grams, what percentage of legal quarters will be rejected? Okay, so you kind of have to make an observation here that if you add 2 standard deviations to the mean, you get one of the values in the problem, 5.81. And if you subtract 2 standard deviations from the mean, you get another key value in the problem, 5.53. And now you can know to kind of do this on problems. You take the mean, add a few standard deviations, maybe see if you're within 1 or 2. In this problem, the values fall nicely to where what we have, like from our picture, if that's our mean of 5.53, the accepted, oops, get rid of that, it's fine. The accepted values here, looks like I'm in like right click mode, bear with me everyone. Okay, try this again. If that's our curve, then here's our mean. Please hold. Let's see. There we go. Our mean, 2 standard deviations to the right, 2 standard deviations to the left. Wants to move it again. You all get the idea. Maybe I'll just work with the picture that's already there and not try to freeform so many sketches here. What we have is the 95% situation. This is what I'm trying to get at. And hopefully, after all the messing around I've done in the last 30 seconds, you kind of get the idea where we're seeing that the accepted values are falling within 95% because the 2 ranges are to the right by 2 standard deviations and to the left by 2 standard deviations. So to answer the final question, how many percent or what percentage gets rejected? Well, if 95% are being accepted by the machine, then 100% minus 95%, 5% should be rejected. Okay. So kind of if this sketch above were of our normal distribution, then the ones that are getting rejected are in sort of this lighter shaded region here. I'll just get rid of those. Kind of this lighter shaded region is like our rejection interval or band, kind of 2 bands there. Okay, so 2.5% of the time you have a coin that weighs too much, and 2.5% of the time you have one that weighs too little, and they get rejected by the machine. Okay. So here are standard scores. What you're talking about here is taking a data value from a normal distribution and giving it a score. From the score, we'll figure out other things, but for now, we're just going to figure out how to calculate these scores for whatever reason. And kind of the very last part of this packet here, which we are getting close to getting through here. We only have 1 more or 2 more examples after this. basically we'll kind of connect the scores to being able to say things about the data values and using our distribution, the normal distribution. Okay, so here's the formula for a z-score. You take the data value you're given, subtract the mean from the data set, and divide through by the standard deviation, where usually on these problems, you'll already know the mean and the standard deviation. Okay, so let's just see this in an example right away. I like this little, this little note here is kind of saying that when the z-score comes out to be positive, that means that the data value is above the mean. The z-score can come out to be 0. We'll see that in a second. It can also come out negative. And so when you're positive, it just means that you're above the mean. When it comes out negative, you're below the mean. Maybe you'll be able to guess what 0 means. I'll show you in a moment. Excuse me. All right, so example 4. The Stanford-Binet IQ test is scaled so that scores are normally distributed. As I said, a lot of standardized exams are designed so that they're normally distributed for these good statistical properties that we're talking about in this packet. Anyway, this normal distribution has a mean of 100 and a standard deviation, so your sigma is 16. So we're supposed to just find the standard scores, or the z-scores, as I call them, as many people call them. So here you would just take the data value. We have 3 scores, 85, 100, and 125. We have to calculate 3 z-scores. We'll start with 85. Here's the data value. It's 85. We're doing minus the mean, which is 100, and dividing by 16. That's the standard deviation. And you'll see in a moment why I'm going to round everything to the nearest 0.05. Here, really the best thing. So if you do the math, it comes out, if you use a calculator, negative 15 divided by 16 is what you get in that numerator, basically, and then that denominator is 16. You get negative 0.9375. Technically, that would round up, if you were rounding to the nearest 0.05, you would round that up to negative 0.95. Negative 0.9 would be acceptable to use here. Okay. The z-score for an IQ of 100. Well, the mean was 100. So you get 100 minus 100 in your numerator, that's 0. You can divide 0 by things. You can't divide by 0. We're not doing that here. We're just doing 0 divided by 16. You can do that in your calculator. You'll get 0. Exactly. And so kind of an interesting thing, right? Like the z-score for the mean should always be 0. So hopefully people will understand what I mean if I just kind of say always, right? Like if you're calculating a z-score for the mean, so you're doing the data value you're given, which is the mean in this case, minus the mean, that's always going to be 0. So keeping that in mind. Before you saw one below the mean, that was 85, that's less than the mean, and sure enough, our z-score came out to be a negative number. Now, we're going to calculate the z-score for something above the mean, 125, and you'll see here it's going to come out to be positive. Okay, so what's the deal with these scores? What you do, why don't we just use one for an example? Let's use this last one. So we'll look up, technically if you're rounding to the nearest 0.05, I think this is the better rounding. The other one is fine, but let's use 1.55. You're about to see why. Oh, and in fact, this one doesn't even go to the 0.05 scale, I guess, but that's fine. So actually, we should probably go to 1.6, which was so maybe we should actually think about get rid of both of those real quick. We should probably actually be working with this one. Anyway, just to show you why these scores sort of matter here. Sorry, I hope I'm not making you all seasick with this scrolling here. So, okay, we had a z-score of 1.6. Notice that this table has essentially 8 columns, but they're grouped in pairs. So you're really looking through it in those columns here. And you look up the score, and that's going to correspond to a percentile. And the percentile tells you how many observations, what percentage of observations lie below your statistic, the one that you're interested in. So for us, we were looking at an IQ score of 125. We calculated the z-score, it came out to 1.6. So the interpretation there would be that 94.5% of people scored less than your score of 125, and that only about 5.5% of people scored higher. Okay, So that's what a percentile means. The percentile means up to that value, that's how many people performed below you. Okay. Now, just one more connection from before. Get rid of some of these annotations, although I did kind of like this was kind of helping me see the 4 columns a little easier. Remember this one, we got a z-score of 0 for the mean. And why would the percentile be 50? Why is it 50 exactly? Well, the mean, right, should be exactly halfway, like smack dab in the middle of a normal distribution. So half the results fall to the left, half the results fall to the right. So if you score the mean on a standardized test with a normally distributed set of results, then certainly 50% of people did worse, 50% of people did better. You're right in the middle. So a z-score of 0 is always going to correspond to that 50th percentile. Okay. So some examples of this now, where we're going to go from z-scores to percentiles and answer some word questions about that. So cholesterol levels, men 18 to 24, so young men, keep that in mind for this problem, I guess. So the cholesterol levels are normally distributed. They have a mean of 178, standard deviation of 41. Again, so another like body measurement of some kind that we're seeing being normally distributed. Anytime you think of these like kind of body measurements, it's kind of like a weird idea, but a lot of them are going to be normally distributed. Same thing with like plants in nature. If you go out and like measure like the petals of sunflowers, that would certainly be normally distributed. So a lot of examples, I should say, in nature. It doesn't all have to be the human body. Okay, for whatever reason, we're looking at a lot of human body things. We're looking at cholesterol here. We'll look at heights in the next one. Okay, cholesterol levels, standard deviation is 41. The mean is 178. So first of all, in what percentile is a 20-year-old man with a cholesterol level of 190? Well, you calculate the z-score. Okay, first of all, let's just talk about what we expect. Cholesterol level of 190, that's higher than the mean of 178. Okay, so you calculate the z-score. It comes out to be positive. It comes out to be like 0.3 if you kind of round up to the nearest 0.1, which is actually what we want to be doing with our table. I said 0.05 earlier. Really, we want to round to the nearest 0.1. Okay, so let's go look that up in the z-table. You're going to see a lot of this like z-table. Oops, just get rid of that. You'll see a lot of these like z-table kind of arrows. It means that I'm looking up the score now. So I have a score. I have a score of 0.3. Let's go to our table. There's where we're at. So this corresponds to the 61st and some change percentile. Okay, almost the 62nd percentile. So that's the answer. In what percentile is a 20-year-old man with the cholesterol level of 190? He's in like roughly the 62nd percentile, meaning that he has a higher cholesterol level than 62% of other men. Okay, so not bad, maybe is like what you would say. I don't know. What cholesterol level corresponds to the 90th percentile? So it's the reverse question. Now you're given a percentile. Okay, at what level, the level at which treatment may be necessary. Okay, sorry, I'm kind of misreading this problem, but basically what they're saying is once you hit the 90th percentile, that's a concern, and then the doctors would want to tell anybody with a cholesterol level higher than that, equal to or higher than that, that they have high cholesterol. So we're going to figure out what value is the breaking point. At what point does a doctor need to say, you know, you have high cholesterol for a man in the age range of 18 to 24. Okay, so we're going to figure that out. Basically, we're going to do the process of part A completely in reverse now. So 90th percentile, right away, we need to go to our z-table. Like, what is the z-score? Okay, so we're going to use the z-table in reverse now. And I'm going to find what z-score is close to the 90th percentile, and it looks like 1.3 is pretty close. That's the 90.32 percentile. We'll work with that, that's fine. Okay, so you'll see that's why I wrote z is approximately 1.3. And so now you have to set up the equation in reverse. You know the z-score is 1.3 for the 90th percentile, or close enough. So the data value is what we want. That's a question mark in this problem. What's the data value? Okay. we know the mean is 178. We know the standard deviation is 41. So you can fill in everything in that equation except for what you want. And so then using algebra, you can get that number. Now, I probably am not going to talk through that, but you can see I have a note here. See how I got this on next page. You can just scroll down to the end here, and you can maybe on your own time just go through this algebra and make sure that it makes sense. Basically, you have to clear the fraction out first, kind of multiply by the denominator on both sides, and then you'll be able to add by 178 to both sides to kind of finish that algebra there. So a little bit of algebra. We try to avoid that in this class, actually, for the most part, but I think that we can handle it in this context here. Okay. So this last example, I'm going to try to go through a little quicker, and I will go ahead and skip the z-table parts, and you can go back on your own and use the table to make sure that what I'm matching it up with actually makes sense and is correct. We're looking at heights now of adult men. Also, again, one of those like measurements that you would expect to be normally distributed. The mean is like very close to 70 inches, which would be like 5'10". Okay. Because 5 feet is 60 inches. So 60 plus 10 gets me up to that 70. So like 5 feet and 10 inches. Right, that's what we're working with as like a mean. Standard deviation is 2.7 inches. All right, so what is the standard score? What are the standard score and percentile of a height of 6 feet? Well, first of all, everything's in inches. So 6 feet needs to be turned into inches. That's what I do right there. 12 inches in a foot. Okay, so 72 inches is my statistic of interest. I subtract off by my mean, divide through by my standard deviation, get my z-score. I have my percentile. As it turns out, 80% of men would be 6 feet tall or less, approximately. 20% of men are 6 feet or taller, is what we just found out. Okay, so in part B, now what's the standard score and percentile of 65 inches? So now we're working with something less than our mean. We get a negative z-score, and we figure out that actually we're talking right now about the 4.5 percentile, close to like the 4.5 percentile, which means that only about like 4.5% of men are 5'5" or shorter. Okay. How about what's the percentage of adult men taller than 6'4"? So now we're getting to a pretty tall height here. First of all, that needs to be in inches, so do that conversion again. You compute a z-score, which is now pretty large. It's larger than the mean. And so you look up that percentile in our table, and you find out that 6'4" is in the close to the 99th percentile. But that's not quite what they asked here. What they asked is what percentage of American adult men are taller than that. So what you have to do then is take the percentile that you found and do 100 minus that. And so really only 1% of men are taller than 6'4". 1.07. Okay. And so looking at the last two questions here, what percentage of the American adult male population is shorter than 5'4"? There you're able to use the percentile value because that's kind of the way it works. And the kind of last one here is interesting about LeBron James and his height. And so you get a z-score that's so large it's not even in our table. You get like 3.8. So at that point, what you all could do on like an exam, or if you're filling this out on your own, is just use the largest z-value in the table. That'd be good enough. But I actually went ahead and went to Google and used the z-table that had a little bit more robust values on either end. And what you find is that LeBron James, his height is in the 99.993 percentile. Now, there's a little bit of math left to finish this question because they're asking about how many men are his height or taller. And so what you have to do is take you turn 99.993 into a proportion, and you have to subtract that from 1. That gives you as a proportion, right now I'm doing a lot of hand waving, but this is the thing I'm talking about here. So you do 1 minus 0.9993. That's the proportion of men who are his height or taller. You multiply by that by the number of men in America. Apparently that's 115 million. Multiply those two values. What you're going to get is the number of men that are his height or taller, and it's only like 8,000 men, 8,050. So that's the end of 6C here. Now, obviously, going a little bit maybe slower than I expected, but not a bad thing to just kind of review these notes, maybe pause the video where you needed to fill things in. Now, if all you missed was Monday, then you can probably tune out unless you're enjoying the video. So moving on to 6D, this is what we did today, Wednesday, the 30th of October, part 2 of Snowmageddon. So this was all about statistical inference, and I kind of was explaining to the class today how, in chapter 5, we did an introduction to statistics that was not focused on calculation. It was mainly focused on like, what is statistics? What are populations? How do we sample? We also talked about, should you believe a statistical study? Now, in chapter 6, so far we've done a lot of calculations of descriptive statistics. So given data, given samples that you've taken, how can you describe a data set to someone? And so that involved mean, median, mode, but that doesn't give you the full picture, which we have seen in many cases. And so there are other descriptive statistics that help give you a fuller picture of what's going on with your data, like range and standard deviation, which tells you about the variation. We also looked at the 5-number summary and box plots. So that's how you visualize your data. So far we've really focused on like taking a bunch of data values and describing them to people, or that sort of part of the process, which is important. But 6D is sort of the other piece of the puzzle that we have not talked about, and it's statistical inference. So going from values like your mean and results from your statistical studies and actually assigning meaning to them, and talking about how they're significant or not. And that may be kind of the more important part of the statistical process. And there's definitely an art to this, and that's kind of what we're going to get into in this packet here. So this packet here, I believe, has like 5 examples, series of definitions, examples. And so I'll try to work through this at a similar pace to what we were just doing there in 6C. So first of all, kind of the guiding definition here, a phrase that we're going to come back to a lot is statistical significance. So this is a set of measurements or observations in a statistical study that would be said to be statistically significant if it is unlikely to have occurred by chance. So I kind of gave you an example right off the bat here, written in blue. This would be like flipping a coin 100 times and only getting heads 10 times. So that would probably not happen just by random chance, versus if you flip a coin and maybe get 55 heads, 45 tails, you can believe that. It's not a hard and fast rule that you have to get 50 of each. Of course, there's deviations from the expectations there, but if I only get like 10 heads or 5 heads or 0 heads, and I flip the coin 100 times, then what you're working with is called a loaded coin, and those do exist, and they're coins that are designed to land on one side more than the other, and you can probably imagine the kind of nefarious things that could be used for. Like, could you imagine if like they used one of those in the Super Bowl, like the scandal that would cause, for example, right? So just kind of having fun with their idea. Okay, but let's go to an example, some from the book, so I don't have to just keep using my imagination here. So, are the following events statistically significant? Explain. So the team with the worst win-loss record in basketball wins one game against the team with the best record. So I would say that's not statistically significant. Sample size is a single game. And by the way, this is why something like, the World Series or the NBA Finals, they don't figure out the results by having them play one game, right? They play a few. And those are for competitive teams that are usually close in talent. Here we're talking about 2 teams with different talent. And someone said, like, how would you actually come up with a statistically significant result in this example? And I would say, well, I mean, the worst team would have to beat the best team several times, maybe 5 times in the season or so. And then you might actually start to think, okay, well, they've matched up 5 times, and this best team has lost to the worst team 5 times. Yeah, okay. And so kind of on the opposite end here, another example. In terms of global average temperature, the 16 years from 2011 to 2016 were 16 of the 17 hottest years on record, using records that go back to 1880. So I'd say this is statistically significant. We're working with about 140 samples here. one from each year, I'd say it's pretty unlikely that 16 of the 17 hottest years would all occur in a row in the last 16 years. You might expect that the hottest years would be a little bit more spread out um, uniformly among those 140 years. That's kind of the point of this question here. So I would say that the fact that they're all occurring in the last like decade and some change would be statistically significant. So do a lot of scientists, by the way. Okay, so I'm not alone on that. So how do you actually quantify statistical significance? It's not just using, statisticians don't just use their feelings for this, they use numbers. Okay, so another definition, it's significance levels. So if the probability of an outcome as extreme as the one you observed is 1 in 20 or 5% or less, then the difference is statistically significant at the 0.05 level, and a very similar definition for 0.01, which I will probably not reread here. So notice one thing here, I've kind of double underlined it in blue. It's 0.05 or 5%, 1 in 20, however you want to quantify it, or less. Okay, so that technically means that if a result or outcome is significant at the 0.01 level, then it's also significant at 0.05. Okay, because 0.01 is also less than 0.05, right? And that would be the reasoning there, but it does not work the other way. So something that's significant at 0.05 is not significant at 0.01 necessarily. Okay, like if it was at 0.03, then that would be okay for the 0.05 level, but it wouldn't be for 0.01. Okay, and it could be a lot less. So if it was a 1 in a million chance of what you observed, then that would be significant at both of these levels. It would also be significant at the 1 in 1,000 level, etc. So hopefully you're getting a feel for that. Of course, the usual thing here, we'll just do an example to kind of illustrate this. So this is a true example, and all these examples, by the way, just came straight from the book. So these I wasn't making them up or pulling them from a different place. These are just our textbook examples for this section, which be helpful for when you go in and do the math lab and the practice problems that I'm assigning. So in 1954, a large experiment tested the effectiveness of a new vaccine for polio. Okay, 400,000 children were sampled, where the population of interest were all US children. So 400,000 people sampled here, children sampled, not people. Half of the sample get a placebo and half get the vaccine for polio. Okay, so among the children who got the vaccine, 33 still got polio. Okay, 115 got polio in the placebo group. So further analysis and calculation showed that the probability of that difference occurring by random chance is much less than 0.01. Discuss the implications and conclusions that the researchers could take away. Are the results significant? If so, at what level? Okay, so the conclusions is that it is unlikely that there were 82 more polio cases in the control group just by random chance, right? We talked about this in class. If it had been closer, if it was like 33 contracted polio in the vaccine group and 35 got it in the placebo group, then no, the vaccine's probably doing nothing. But the initial conclusion here is that the drug looks to be effective, is what I would say. So yes, the results are statistically significant because it doesn't seem like this would happen just by random chance. And further, what we can say from the calculations that they gave us is that the result or the outcome is significant at the 0.01 level because it could have occurred by random chance only much less than 0.01 of the time. Okay, so in that problem here, it just kind of shows you're not going to be asked to calculate the significance value. You just have to, given information, given the values like 0.01, well, much less than 0.01, 115, 33. You use these given values. You don't have to go conduct the statistical study yourself, and you don't have to calculate these numbers. Okay. So another definition, margin of error. This is just an approximation. We've seen approximations to all different kinds of things in this class. This is just a way of approximating a 95% confidence interval margin of error. What you do is you just take 1 and you divide it by the square root of the number of samples. Sure, let's just see how it works. So example 3, find the margin of error and 95% confidence interval in the following survey. By the way, you'll want to do it in that order. We need to get the margin first, and then we'll make the confidence interval. So survey of 500 people finds that 52% plan to vote for Smith for governor. Great. The margin of error is going to be 1. Well, the approximate margin of error is going to be 1 divided by the square root of 500. And if you do that in your calculator, you'll get like 0.04. So remember, with confidence intervals before, we were usually just given the margin of error in these problems. Like I will just tell you, oh, hey, the margin of error, it's 0.04. But here we actually just calculated it for ourselves using an approximation. Kind of an interesting thing to use. So to set up the confidence interval, you have to do 52 minus the margin of error and then 52 plus the margin of error. And what you'll get at the end of the day is the kind of circled answer here, which is that the true value 95% of the time would lie between 51.96 and 52.04. So I'm just adding and subtracting and adding the margin of error to that statistic that they gave us. So the conclusion in this problem is that this candidate is very likely going to win based off of this survey, which has a decently large sample size, and the confidence band is tight around 52, and the confidence interval does not include any values that are less than even 51.96. So what that means, to win an election, you need 50% or greater, and this candidate with 95% confidence is going to have a result between 51.96 and 52.04. So a good poll for this candidate would be the conclusion here. Okay, so this last part, a little bit confusing, but again, it's going to be sort of the usual thing where the definitions might seem a little weird at first, but then we'll just jump into an example that will hopefully just kind of clear it up. So, kind of bear with me here, but another kind of set of definitions. So the null hypothesis, we're talking about hypothesis testing here for kind of the remainder of the packet. So the null hypothesis is a starting assumption for a hypothesis test. And there are many different forms that a null hypothesis can take, but for our book and for our class, we're just going to consider one type, where the null hypothesis is basically going to say that some population parameter that we want to talk about equals some number. Again, this is all going to be very abstract at first, but we'll kind of tie it into some examples. The alternative hypothesis is going to be a claim that the population parameter has a value different than what's claimed in the null hypothesis. So it could be greater than the claimed value or less than the claimed value. So usually in studies, you come up with a null hypothesis and then you try to break it. You're trying to prove that the null hypothesis is untrue. And this is usually the standpoint that statisticians take for many reasons. One being that you want to always be of the viewpoint that what you're doing has no effect, and then you try to disprove that. So kind of thinking back to our clinical trial for a vaccine, the null hypothesis would kind of be no effect, that the polio cases would just be equal to what you would have in the control group. But then what the researchers are of course hoping to do is show that in fact that the number of cases is much less than what happens when you do nothing. That's kind of the idea here. So a little example there in words, but let's actually go into a more detailed example. So a dog food company claims that its special diet mix will allow a certain breed of dogs to live to a mean age of 15 years, which is significantly longer than the overall mean longevity for the particular breed. Now, a consumer group says that this claim is overstated and that the actual mean will be less than the company's claim. So state the null hypothesis and alternative hypothesis for a hypothesis test. So the null hypothesis here is that the mean age for the dogs eating the diet mix would just be 15 years. You're from the viewpoint of the consumer group, that's kind of the assumption that they're going to try to disprove. And that's the way the null hypothesis usually kind of works here. So again, the mean age for the dogs eating that diet mix, you're going to say the null hypothesis is that it is in fact 15 years. The alternative hypothesis, what this consumer group would hope to show, is that actually the mean age for the dogs eating the diet mix is less than 15 years. That's it. That's the answer for this problem. That's the null hypothesis along with the alternative hypothesis. They're never going to ask for just one. They're always going to ask you for that pairing. Okay, so that would be the hypothesis test that they would set up and try to work with in that case. So one more kind of pair of concepts here and an example, and we will be done. So thanks for hanging in there if you're still watching. Okay, so two possible outcomes of hypothesis testing. Number one, and I've already kind of talked about this a little bit now, but the first outcome is that you reject the null hypothesis because you have evidence in support of the alternative hypothesis. This is usually like a good thing, okay, if you're doing a study. And then the second outcome is that you fail to reject or do not reject the null hypothesis. This happens when you lack sufficient evidence to support the alternative hypothesis. So this can happen. And researchers do have to be honest about that when it occurs. So let's talk about the kind of test decisions and how you end up at either outcome using, again, not feelings, but like numbers. And this is how statisticians make these calls. So we decide the outcome of a hypothesis test by comparing the actual sample statistics of, in example 4, like the 15-year mean dog age that this company is like claiming, probably without valid reason, to the statistic expected if the null hypothesis is true. Okay, and actually I think I got that backwards. So the statistic expected if the null hypothesis is true, that would be that the mean dog age is 15 years. And then the actual sample statistic, that's what that consumer group would go figure out. And they would try to show that that's less than the 15 years, which would mean that the null hypothesis is not true. Okay, so if the likelihood or probability of a sample statistic, at least as extreme as what you observed, is 1 in 100 or 0.01, then we are going to call that significant at the 0.01 level. And so we've already seen that definition, but this significance, what it means, it offers you strong evidence for rejecting your null hypothesis and accepting the alternative hypothesis. Now, if you're significant at the 0.05 level for a result, then that significance level offers only moderate evidence for rejecting the null hypothesis. It's still, you can still reject it. You just have to clarify that it's only at the 0.05 level, which for like a medical study, that would not be acceptable. Okay, like for a vaccine, that would be totally not unacceptable. They would be working with confidence levels probably much less than 0.01. Okay, and if that likelihood or probability comes out to something above 0.05, the result is not statistically significant and therefore does not provide sufficient grounds for rejecting the null hypothesis. Okay. One last example, just to kind of illustrate what's going on here. I liked this example, thought it was a pretty interesting one in terms of what we're working with. So you have a county health official that believes that the mean birth weight for male babies at a local hospital is greater than the national average of 3.39 kilograms. Now, a random sample of 145 babies at this hospital that the official is making a claim about has a mean birth weight of 3.61. Okay, so it's greater by like 0.2 kilograms and a little change, 0.22 kilograms. Assuming that the mean birth weight of all male babies born at the hospital is the national average of 3.39 kilograms, a calculation shows that the probability of selecting a sample with a mean birth weight of at least 3.61 kilograms is only 0.032. That's the probability of randomly getting that mean of 3.61, which is greater than the national average. So first of all, what's the null hypothesis here? What's the alternate? So the null hypothesis is that the baby's average birth weight at this hospital that the official is making a claim about is only 3.39 kilograms. So the null hypothesis is that no, the official is wrong, and actually the average birth weight equals the national average even at this hospital. The alternative hypothesis, which they're trying to verify, is that the baby's average birth weights are in fact larger, so greater than 3.39. That's the alternative hypothesis that they hope to show. Okay. Discuss whether the sample provides evidence for rejecting or not rejecting the null hypothesis. So we do have evidence at the 0.05 level to reject the null hypothesis, and we would accept the alternative hypothesis. How come? Well, it's because the observed difference in weight only would happen by random chance 0.032 or 3.2% of the time, which is less than 0.05 or 5%. So that was the number they gave us. Again, you're not going to have to calculate that 0.032 number. It was just given to us in the problem. Okay, and so what it means is that only randomly would you get this increased birth weight only 3% of the time would you get this increased birth weight by random chance. Okay, so finally, just note that we do not have the evidence here to reject the null hypothesis at the 0.01 level. Okay, so if they were going to go write a paper for Nature or for the Scientific American or some amazing science journal, this might not make it in there because it's just not quite significant enough, and probably what they would ask for is more samples, more proof, more evidence, and a higher confidence interval, which you might be able to show by really taking the average of more and more of these babies. But probably what you would find out is that it would get closer and closer to that national average over time. Who knows? But for this problem, these are the answers. So that's the end of 60. And I think in the interest of not making this video file absolutely humongous, I better just cut myself off here. But if people have questions, definitely via email or on Monday we can discuss. But hopefully this helped kind of make up for those of you who weren't able to make it to class this week or to either class. So I will go ahead and end our meeting, and thank you for watching.